All right, we're back again with some more derivatives, and today we're going to look at exponential derivatives and logarithmic derivatives. And we're actually even going to use a lot of the chain rule today as well. So we'll get a little refresher on that. So let's go ahead and just jump right into some exponential derivatives. And like the power rule being used for polynomial functions, this is a rule that we're going to use for exponential functions. So it's different from the product, quotient, and chain. Those were more like strategies. Today, we're looking at the exponential and logarithmic derivative rules. So this is the exponential rule. And all that it says is that if you have a function that looks like a to the x, so it has some base a, and that a is just a constant, some number, it's 2, it's -4, it's E, we might see that fun letter E, could be pi. There's a couple fun letters and numbers that we like to use there, but it is a number, that A, and it's raised to an exponent that is a variable. If that's an exponential function, then the derivative says this: we copy it, it's just a to the x, we just copy it down exactly as it is, and then we multiply by the natural log of a, which is again that constant. One thing that a lot of people like to do, I almost don't want to mention this just so I don't get into your heads, but a lot of people do it anyways. They put an x here instead of an a. Don't do that. Make sure that this is always a constant. It's always ln of a, ln of a constant there. So just a very quick example here. If I said, hey, f of x is equal to 2 to the x, then f prime of x would just be 2 to the x ln 2. And it's really just that simple. You just copy it down and then you multiply it by ln of whatever that base is. If I had, let's say, g of x is equal to pi to the x. Remember, pi is a number, 3.14159, it keeps going on. G prime of x would be equal to pi to the x, I copy it, times ln of pi. And there we go. Great, so let's go ahead and move on. There is a specific type of case here. There's a specific type of exponential that we deal with a lot, and that is what we call the natural exponential, and that's with this fancy e. And e is very similar to pi in the way that it likes to live its life. It's just e just stands for a number. It's 2.71828, and it just keeps going on forever and ever. Very, very similar to pi in that it's, it just goes on forever. It never repeats itself. It's what we call an irrational number. But we've got that e there. So whenever you see e, that's that number. That's 2.71 roughly. So if we take a derivative of my function e to the x, as opposed to like 2 to the x or, pi to the x or 3 to the x or, any of these, when I see e to the x, I don't do anything differently. I copy it, e to the x, and then I multiply by ln of e, and because e is that base, that constant down here that I'm going to multiply by. So this part right here should look exactly similar to this right here. It's the same exact thing. The only difference here now is that we actually know what ln of e is, and ln of e is actually equal to 1. So you don't have to bother writing it. You can just write e to the x, and this is a perfectly acceptable answer, e to the x. And so what a lot of people will just remember is, hey, the derivative of e to the x is just e to the x. That's just what it is. It's just the function itself. I just copy it down. Sometimes what some people do is they will write ln of e, and then they'll simplify it to e to the x because we know that ln of e is equal to 1. That's fine. That's totally okay. I don't really care what you do, but just remember that when it's e, it's nothing special. It's no different than if I put 2 to the x. Like on this example down here, it's no different. It's just that here I don't actually know what ln of 2 is. It's just ln of 2. It has a value, I'm sure, but we don't know what it is off the top of our heads. We do, however, know that ln of e is equal to 1, so we can do some simplification there. So let's go ahead and jump into an example, and I'm not going to use the natural exponential. I'm going to have a base of 4. And what we should see here, we have 4 raised to the x squared plus 3x. The first thing that you should notice here is that this is not going to be a very simple derivative. It's not going to just be a simple application of the exponential rule. And that reason is because that the exponent is more complicated than just an x. It's an x squared plus 3x. So this is actually an inner and an outer function scenario. So we're going to have to use the chain rule here. And so when we use the chain rule, as we always want to do, we want to identify the inner function and we want to identify the outer function. And so let's go ahead and write these down. Inner equals x squared plus 3x. And the outer is just 4 to the x. 4 to the blank, if you will, 4 to the red blob, like we saw in the last lecture, but it's 4 to the something, and I'll just say 4 to the x to keep it simple. So when I do my chain rule, remember that I have f prime is equal to u, and let me go ahead and label these. U is my inner, v is my, u is my outer, and v is my inner. So I'm going to do u prime of v multiplied by v prime. So it's just that inner derivative out here, and I'm multiplying that by the outer derivative out there. And so when I actually do this, I'm going to take u prime, which is my outer. So I have my outer function is 4 to the x. Well, we've just learned how to take a derivative of 4 to the x. I write down 4 to the x, I just copy it, and I multiply it by ln of 4. And boom, that's it right there. We have our exponential derivative that we've taken care of yet. But what we got to be careful about is this v of x, right? Remember, we said we leave the inner unchanged. I don't want to write an x here. I want to make sure that I write x squared plus 3x. So let's go ahead and do that. So as we can see here, I have that format of, let's go ahead and write this down in the corner, d dx of 4 to the x equals 4 to the x ln 4. That's the rule that we've just learned. But then I'm just making sure that I'm putting x squared plus 3x. I'm leaving that inner function as it were, rather than writing something different. So I'm not done. I still have to multiply by the derivative of v, which is the inner function. And when I multiply by that derivative, I'm going to have 2x plus 3 for the derivative. And that's just me taking a derivative of x squared plus 3x using the power rule there. At this point, we're pretty much done. You could rewrite this in whatever way you wanted to make it look a little bit simpler. But this to me looks about as simple as you can make it. I can't tell you off the top of my head what ln of 4 is, like without a calculator. I wouldn't want to bother distributing this in at all because that's just going to give me a bunch of different terms. It really just looks about as simple as I can make it here. So we'll just go ahead and leave it right like that. Let's go ahead and box this so we have our answer there. Boom. So we've got that right there. So that's using the chain rule as well as using this new exponential rule that we've learned down here. So let's go ahead and move on to logarithmic functions. And again, we're going to start off general here. We're going to start off with log base b of x. And so reiterating that again, log base b of x. So this b here is called the base. That's why I give it the letter b. Just a quick reminder before we jump all into this. If I write log of x, that is exactly the same. Means it is exactly the same as log base 10 of x. It's just a shorthand way of writing it. Basically, log base 10 pops up so often that we just, a lot of times we just kind of say, hey, let's not even bother writing the 10. And if we just write log of x, that means log base 10. It's kind of like a hidden 10 right here. So one other piece of info in terms of naming things, if we write ln of x, that means log base e of x. Let's go ahead and put some parentheses here too. A lot of times you don't have to put parentheses around these. I'm just going to now, just to be clear. So natural log of x, ln of x, it means the exact same thing as log base e of x. Basically, log base e of x pops up so often that we just give it a shortcut name here, ln of x. Just to be very clear with how I say things, a lot of times when I'm talking about ln of x, I'll just say log of x. I know that can be confusing because you might think that I mean this. So try and take my verbal saying in context. If we're talking about natural logs, if that's all we've been dealing with, if the problem has natural logs in it, and you hear me just say log, this is probably what I mean. Really, the reason I do that is because outside of business applications, whenever someone talks about logs, they really generally mean a natural log. A natural log pops up so much more often than regular logs in real world, in real life scenarios, that we just say log when we generally mean natural log. I'll try and be careful about that, but just be careful, think about the context of the problem and what I probably mean. So let's move on here. We've got a function here that I want to take a derivative of, log base b of x. So whatever that base is, it could be anything. It could be any number. It could be e, it could be 10, it could be pi, it could be 7, whatever it could be. If my function looks like this, when I take a derivative of it, the first part is that I have a 1 over x. And then so 1 over whatever is on the inside here. In this case, it's just an x on the inside right there. So I have 1 over x, and then I multiply that on the denominator by a natural log of the base. And again, don't put an x here. A lot of people will just flip these. They'll do 1 over b ln of x. That's bad. We want it 1 over x times ln of that base right there. And remember, this ln is just log base e, but it's just a shorthand way of writing that. So we come to, again, like we saw before, this is the more general case, but you might have a natural logarithm. And so if I give you the derivative of ln of x, remember that this is exactly the same as writing log base e of x. It's no different. It means the exact same thing. So I do my derivative the exact same way. I do my 1 over x, and then I multiply by ln of the base, which in this case is e. But yet again, we see this sort of pattern here. This ln of e is equal to 1. So I can just simplify to just get 1 over x. And so this is sort of a shorthand thing that we'll remember. The derivative of ln of x is just 1 over x. So you're welcome to just use that shortcut and just go right into that if you want. You're welcome to write it out fully and explicitly like I have in the blue box up there. But this is fine. I'm okay with you guys going, jumping between these two steps here. So yeah, there we go right there. That's just kind of a specific case of the logarithmic derivative. So let's go ahead and do an example here. We're going to stick general. We're going to have a base of 3, and we're going to have log base 3 of square root of x. Again, we're going to have to use the chain rule here. I have an inner and an outer function, right? This inner part here, this square root of x, is more complicated than just a regular plain old x. So I'm going to have to deal with that inner function in the chain rule sense. So let's go ahead and say v is my inner function. and u is my outer function. And that's log base 3 of x. I'm going to go a little bit quicker here on the chain rule just because we've been dealing with it a bit now. So I'm going to do the derivative of the outer part first, and I'm going to leave the inner completely untouched. So when I do the derivative of that outer part, that's the derivative of log base 3 of x. And let's remind ourselves that the derivative of log base 3 of x is equal to that 1 over x ln 3, right? So now, when I do the derivative of this outer part, I'm going to have a 1 over, not an x, but a square root of x. Remember, I'm leaving that inner part untouched. So it's 1 over whatever's on the inside there, multiplied by ln of 3. And so that should look, that right there should look nearly identical to that. The only difference is that because I'm doing the chain rule, I have to just leave that inner root x completely untouched. I don't want to put an x down here because we actually have an inner function and it's root x, and that's what the chain rule tells us. Now the chain rule also tells us that I have to multiply by the derivative of the inner function, and we've been dealing this for a while now. The derivative of root x is 1 over 2 root x. I personally, I've said this before, I like to just memorize that. It pops up so often that I just like to memorize it. At this point, I can actually do a little bit of simplification. Those root x's can multiply to just become an x. So we'll have 1 over 2x ln 3. We'll box that as our answer and we're done. And so there's some more chain rule with that natural log. Just reminding ourselves that natural log, I'm always doing 1 over whatever's on the inside, and then also divided by natural log of that base, that constant, that 3 in this example right there. Great. Let's go ahead and look at one more example here. And when I see this, I immediately have that sense of, okay, let's jump in and let's just like do our derivative. I see my ln, I know that that's a log base e, so I can just utilize this quick formula that we've seen already. ddx of ln of x, it's just 1 over x, right? So I can just do 1 over all this stuff and we're on our way. But the problem is I then have to do the chain rule, right? Because again, this is an inner part and this is an outer part right here. So yeah, I can do the derivative of my outer part, leaving the inner part untouched. So I can do my 1 over all of this. I can write that out. 1 over x cubed over square root of x times x minus 1. But then I'm going to have to multiply by whatever the derivative of x cubed over square root of x times x minus 1 is. And that looks horrible. That looks really ugly. I don't want to do a quotient rule and then even within that quotient rule do a product rule. That just sounds really bad. And so doing our normal logarithmic rule here is not going to be very helpful because it's just going to take us a very long time, and there might be a quicker way to do this. And there in fact is. I wouldn't be saying all of this, you know, in such of a tone as I am if there wasn't a quicker way of doing all this. And that faster way is to use log rules, logarithmic properties. I'll go ahead and leave that there. We might use that in a bit. What I'm going to do is I'm going to rewrite this function using logarithmic properties. And hopefully we can remember those. If I have things that are divided by each other, I can subtract them. So that's that log property there. I'll go ahead and write this up at the top here in red. Logarithmic properties. If you're not familiar with these, go ahead and look them up on the internet or something like that. They're definitely important to know. I will ask you about them. You will have problems on them. like we're doing now. So logarithmic properties, if you have a natural log, or any log for that matter, of two things that are divided by each other, you can subtract them. And then another rule is that if I have two things that are multiplied by each other inside a natural log, I can actually add those together. And there we go. Now I'm going to do two things here. I'm going to use a third log rule, which says that if I have an exponent inside that logarithm, I can bring that out. I can sort of drop that down to the front there. I'll leave that written in there. And I get my 3 ln of x. I'm going to distribute this minus sign out. Notice here that square root of x is an x to the 1/2. So I can go ahead and drop that down as a power using the log rule for powers. Distribute that minus sign. Nothing I can do on this x minus 1 there. One last little simplification here. I have 3 ln of x minus 1/2 ln of x. Those are common terms, so I can subtract those down to 5/2 ln of x minus ln of x minus 1. And there we go. We are on our way right there. We haven't even taken a derivative yet. That's fine. But we actually, we can simplify this a lot more before actually taking our derivative. And so there we go. We've got our function right there. Let's go ahead and take an actual derivative here. And I'll go ahead and copy this. Onto a new page here. All right, so this is our new f of x. It's, well, I shouldn't say new. It's the same f of x, but it's just rewritten, just simplified a lot. And if I want to take an actual derivative here, put this in a different color. If I want to take an actual derivative, I'm just going to use my derivative rules. So we'll have 5/2. And then remember, when we have ln of x, we've got that sort of shortcut that it's just 1 over x minus, now I have ln of x minus 1. So I'm going to have to use the chain rule here because my inner function is that x minus 1. It's more complicated than just an x. So I have to use the chain rule. So I'm going to do a derivative of the outer part, which is my natural log. And that outer part derivative tells me I do 1 over whatever's on the inside. I leave that inside untouched. So I just have 1 over x minus 1. Then I have to multiply by the derivative of the inner part, which is just x minus 1. Well, that derivative of that x minus 1 is just 1. There's just a simple application of the power rule there. This is just 1. There's nothing really more complicated to it. So in a problem like this, you'll start to get the hang of this, where when you just see x minus 1, you'll kind of realize, hey, I'm technically using the chain rule, but there's really nothing else I have to do. It's just that derivative ends up being just 1 right there. So nice and simple. Let's do some simplification. We've got 5 over 2x minus 1 over x minus 1. At that point, you could call it here if you wanted to. I would say it would be a little bit more simplified to actually find a common denominator. So let's go ahead and do that. Let's multiply by x minus 1 over x minus 1 here. Let's go ahead and multiply by 2x over 2x. And when we do that, we're going to have 5 times x minus 1 minus 2x all over 2x times x minus 1. I'll just sort of move to the right here now. 5x minus 5 minus 2x all over 2x times x minus 1. And this ends up being 3x minus 5 all over 2x times x minus 1. And there we go. That answer to me looks a lot more simplified than this case here where I have two different fractions being subtracted by each other. So I like this format a bit more. Not to say that this is bad per se, it's just this is a little more simplified down here. So there we go. We've got our derivative there. So that's going to be this example is going to be doing logarithmic derivatives using log rules to simplify your logarithm before taking your derivative. So just as a recap, let's go ahead and put these all back in perspective. So we've got d dx of a to the x is just a to the x ln of a. We have this special little case here, d dx of e to the x. It's still the same rule. It's e to the x ln e, but ln e happens to just be 1, so we just write that. And then we've got d dx of log base b of x being 1 over x ln b, with this slightly special case. When it's a natural log, we can just do 1 over x ln e, which again, that ln e is just 1, so I can just do 1 over x. But right there, that's pretty much the entire lecture simplified into four little rules right there. And there we go. So again, just one last thing to mention, if those log properties are fuzzy to you or if you don't remember them at all, look those up. Those will be very important. We will use those. So definitely make sure you know those well. And I'll go ahead and leave it there and we'll call that for the lecture.